Okay, let's look at question 5 from November 2016. Hydrogen peroxide decomposes to produce water and oxygen according to the following balanced equation. 2 hydrogen peroxide goes to 2 water plus oxygen gas. The activation energy for this reaction is 75 kilojoules and the heat of reaction delta H is minus 196. Define the term activation energy. So this one we can just get from our notes or the exam guidelines. So they accept the minimum energy needed for a reaction to take place, but I think the exam guidelines say it's the minimum energy needed to form the activated complex. Either one will work. Now it says, redraw the set of axes below in your answer book and then complete the potential energy diagram for this reaction. Indicate the value of the potential energy of the following on the y-axis: the activated complex and the products. The graph does not have to be drawn to scale. So now on this curve, I've actually got the curve out the memo here because I can't draw on the screen. It's very irritating. The main thing is, first of all, look at this. This is an exothermic reaction. So you go to the curve that they gave you, you draw in an exothermic reaction. Any exothermic reaction, so long as you've got a flat bit by the reactants, it goes up the activation energy hill, comes to a peak, comes back down, and flattens out with the energy of the products. So reactants, products. Activation energy is the amount of energy to get up to the activated complex. So this is not actually zero, but if we take it as the zero reference, remember we can take anything as a zero reference. So if we put this as the zero reference, then activation energy is 75 kilojoules above this. So this is going to be 75 kilojoules because it takes 75 kilojoules of energy to form the activated complex. And then the delta H, the heat of reaction, is minus 196. Delta H is the difference between products and reactants. So it is this value between the line for the reactants and the line for the products, and it is negative 196. So if you take your reactants as 0, 75 kilojoules to get up the energy to get to the activated complex, you then go down the hill again and you end up with a total of minus 196 from your zero reference. So your graph must look like this, and that's how you fill the values in. And you just put 0 there, even though it's not technically the energy of the reactants, but it works for the purposes of this question. You've taken the energy of the reactants to be 0. So when powdered manganese dioxide is added to the reaction mixture, the rate of reaction increases. So powdered manganese dioxide is that black powder. It's a catalyst for this reaction. On the graph for question 5.1.2, use broken lines to show the path of the reaction when the manganese dioxide is added. Now all manganese dioxide is going to do as a catalyst is make you have a lower activation energy. It will not change the energy of the reactants. It will not change the energy of the products. So you make sure that you go past this part where it's flat, where the energy of the reactants is, and then you draw in your dotted line so that it meets somewhere on the slope here. So you could draw in this and that, but at the end of the day you cannot change this, you cannot change that. You just draw in this little dotted peak at a slightly lower value than 75, and there you're done. So now it says use the collision theory to explain how manganese dioxide affects the rate of decomposition of hydrogen peroxide. So we need to say here hydrogen peroxide is a catalyst. It provides an alternate lower energy reaction path for the reaction. This lower activation energy, goodness my typing, this lower activation energy means that more reactants have activation energy or greater. This means that there are more effective collisions. Remember the effective collisions and what goes with the effective collisions per unit time. There are more effective collisions per unit time, which means that the rate of reaction increases. So we've mentioned that lower activation, we've mentioned that the catalyst provides a lower energy reaction path with a lower activation energy. We've mentioned that there are more reactant particles that have lower activation energy, that have the activation energy or greater. So then we have mentioned the more effective collisions per unit time. So then the rate of reaction increases. Okay, graphs A and B were obtained for the volume of oxygen produced over different times. Calculate the average rate of reaction in cubic decimeters per second between t equals 10 and t equals 40 for graph A. Okay, let's just look at these two graphs quickly. So graph A definitely had the higher rate of reaction than graph B, but both of them flattened out at 60 cubic decimeters of oxygen, which means that they must have had the same amount of reactant to start with, because the curve would be higher if there was more reactant. So it's the same amount of reactant, just this probably catalyzed, this is not catalyzed. So let's calculate the average rate of reaction between t equals 10. Okay, so let's have a look here at t equals 10, v equals, what do we read off the graph at 10? Okay, 1, 2, it's in the middle here. 1, 2, 3, 4, 5, we go up here. No man, where's the middle here? 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks, and we go up 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks. I would say 6 blocks here. Okay, so I'm going to say the volume is 16. Okay, at t equals 40, at t equals 40 up here, it looks like 52. At t equals 40, v equals, is that right? We are on graph A, hey. Yeah, at t equals 40, I would say that's 52. I hope my eyes are not too old for this. Okay, so average reaction rate equals the change in volume over, remember to do it as a fraction, the change in time. So my average reaction rate is going to be, what's the change in volume? Final minus initial, am I right? 52 minus 16 over the change in time. Make sure you show this, don't do mental arithmetic and say over 30. Show that you've known the difference in time. Make sure you set this out as a fraction. Use your calculator. What is 52 minus 16? 36 over 30. So my average reaction rate is going to be 1,2 cubic decimeters per second. Okay, it takes me ages to type those units in. Okay, so I think that's the correct answer to that question. Goodness me, we hope so. Okay, use the information in graph A to calculate the mass of hydrogen peroxide used in the reaction. Assume that all the hydrogen peroxide decomposed. Use 24 cubic decimeters per mole as the molar volume of oxygen. Okay, so we're going to have to find the moles. So we know we're going to use N of oxygen is going to be equal to V over Vm. So how will we find the number of moles of oxygen? We have to read off the curve. Okay, the total number of moles of total volume of oxygen that was produced here was 60 cubic decimeters, sorry. And they said to you, what's the molar volume? 24. Okay, so my number of moles of oxygen, calculator, I've got 2.5 here. Hopefully we've got the right answer. Okay, I've got 2.5 moles of oxygen. Now we need to have a look at the mole ratio, because were we asked to find oxygen? No, we were asked to find hydrogen peroxide. So the mole ratio of oxygen to hydrogen peroxide, where's my balanced equation? 2 hydrogen peroxide to 1 oxygen. Okay, so if we wrote this the other way, it's 1 oxygen to 2 hydrogen peroxide. Am I right? Yes, 1 oxygen, 2 hydrogen peroxide. So you're supposed to set this out more neatly, but we're running out of page. Okay, so if we've got 2.5 oxygen, the hydrogen is going to be times by 2, which is going to be 5. Okay, I reckon that we've got 5 moles of hydrogen peroxide. It says to you, what are you supposed to find? The mass of hydrogen peroxide used. So mass of hydrogen peroxide, we're going to have to use N equals M over M, but we're going to go M equals N M. So the moles of hydrogen peroxide is N5 times, what's the molar mass of hydrogen peroxide? Let's work it out here. 2 plus 2 for the hydrogen, 2 16s is 32, so that's going to be 34. We're just going to write 34 in there. So 5 times 34, I've got 170. The mass of, did I write water here? How did I write water? The mass of hydrogen peroxide is going to be 170 grams. Okay, and that should be my final answer here. How does the mass of hydrogen peroxide to obtain graph B compared to that used to obtain graph A? Choose from greater than, smaller than, or equal to. Well, graph A and graph B produce the same amount of oxygen, so according to the law of conservation of mass, it must be equal to, because if there was more, there would be more oxygen. If there was less, there would be less oxygen. Okay. 3 energy distribution curves for the oxygen produced under different conditions are shown in the graph below. These are your Maxwell-Boltzmann curves. The curve with the solid line represents 1 mole of oxygen gas. Choose the curve P or Q that each represents the following situations. 1 mole at 90 degrees, 1 mole at 120. So average kinetic energy is where the peak is, and that's your temperature. So which one? These 2 peaks are in the same place. These are at the same temperature. So it has to be Q, because Q has the peak further along. 2 moles of oxygen gas produced at 90. If the temperature is the same, the peak is at the same kinetic energy. This one has to be P. And I do believe we are done with this question.